Hello everybody and welcome to Capacitors lesson 5. Now in the last video we had a look at the time constant, and just to remind you, actually if we go back to lesson 3, we had the equation, the discharge equation, Q is equal to Q naught E to the minus T over RC, and the time constant was that bit there, it was the R times C. And obviously from there we had a look at the various different uses and how we can use that time constant in a lot of ways to make our calculations a lot simpler. In this video then, what we're going to move on to, hopefully just to round everything off at the end of this topic, is we're going to have a look at charging capacitors and the equations that go with that, and then we'll finish off just with looking at capacitors as other electrical components in series and parallel with each other. Now, in order to have a look at the equations, or obviously the graphs as well, with how we charge capacitors, firstly let's just remind ourselves about discharging capacitors. Obviously we would have had a capacitor with a certain capacitance, and that would have been discharged through a resistor, which would have had some known resistance. That would be our discharge circuit. For charging then, we obviously need some kind of supply, some kind of energy supply, some kind of battery cell, whatever you want to call it. So there we go. And we'll still have our capacitor, because obviously that's what we're trying to charge. And we will normally have a resistor in that circuit as well. So we've got our source that will have a potential difference of V, and we've still got a capacitor of capacitance C, and we've still got a resistor of resistance R. So that then is the charging circuit. Now let's just remind ourselves of what's going to happen when we charge. We know that current, or conventional current, always flows positive to negative, but that means the electrons are going to flow negative to positive. In other words, it's this end of the capacitor that will end up negatively charged, and this side of the capacitor that will end up positively charged. Initially then, what we're going to say, so obviously when we do our initial values, we're saying when T is equal to 0. Well, at first we're going to say that the capacitor is completely discharged, and therefore the charge on the capacitor will be 0. Of course, if the charge on the capacitor is 0, then the potential difference across the capacitor will be 0 as well. So let's just make sure we make that distinction. That's across the capacitor. In other words, if we had a voltmeter and we put it there across the capacitor. The last thing that we need to have a look at is the current. So let's just put an ammeter there, of course, in series, in order to measure the current. Well, at first, because the capacitor isn't holding any charge and the potential difference across it is 0, at that point you can almost, from the initial point of view, you can almost ignore the capacitor, and all you've got is a basic series circuit with a source, a potential difference, and just that one resistor in there. In other words, the current will be at its maximum value, and we can calculate that using Ohm's law, V equals IR, or obviously we can rearrange to say that that is V over R. But the whole point is that current is going to start off when T equals 0, when we initially connect this circuit together, or if we put a switch in there, when we initially connect the switch, that current will be at its maximum value, and you'll see why it's its maximum value again, and we can just calculate it by using V equals IR, where obviously this V that we're calculating here is going to be the potential difference of the source. Bringing that circuit across to a new slide then, so we know that when t is equal to 0, we said that Q will be 0, we said that V will be 0, and we said that I will be V over R. And just remember the two different V's. This is the V that I've done in green, the V across the capacitor, whereas this one here is the V of the supply. Now we know that when we connect the circuit up, we're going to get a current flowing, and that's going to cause charge to be stored on the capacitor. So as T increases, well, we know that Q will therefore increase as well, because that's the whole point. We're trying to charge the capacitor, we're trying to get charge stored on the capacitor, and that will also be proportional to the current as well. Now, of course, if the charge increases, then the potential difference across the capacitor will also increase as well. And we also know that that is going to be proportional to the charge that we've got on the capacitor at any given time. Now, for the current that's flowing through the circuit, we do need to look at this slightly differently. As the capacitor gains charge, we know that it has a potential difference across it. But what you can see is that the positive end of the capacitor is pointing towards, if that's the right phrase to use, is pointing towards the positive end of the supply, and so is the negative end. What that's going to do, if we just remind ourselves, we go back to some basic ideas from DC theory. If we have two power supplies that are pointing in the same direction as each other, so if we've got V1 and V2, then the total potential difference is V1 plus V2. If we were, though, to change the polarity of one of them, then what we end up with now is V1 minus V2. In other words, by having one of the supplies facing the other way, so negative to negative, the way that I've drawn it then, the total potential difference in the circuit, or in that combination, is going to decrease. Now, exactly the same is going to happen with our capacitor, because the positive is pointing to the positive end, because the negative is pointing to the negative end. What we end up with is a situation very similar to the bottom one, where we have two cells down here. Now, what that's going to mean is the total potential difference in the circuit from both the supply and the capacitor will end up decreasing. And because that decreases, it's going to cause the current to decrease as well. Now, the amount that current decreases by is going to depend on what the potential difference across the capacitor is, and that, we know, depends on the charge on the capacitor as well. So really, that current drop, that decrease in current, is going to be proportional to the charge as well. Now, we can see, without doing any maths on this, we can already see that we've got this cyclic argument again, that the charge depends on the current, but the current depends on the charge. One's affecting the other, one's causing the other to increase or decrease, and therefore, whenever we see that kind of argument, that one thing affects the other, which then affects the first thing, we're always going to get an exponential out of it. If we think about the current first then, well, the current's going to decrease. So current against time, the current will decrease exponentially, and will therefore, if we take I naught, which of course is this one up here, that will just be governed by the equation I is equal to I naught E to the minus T over RC. That one shouldn't really be a surprise to you. Now, for the charge, and therefore by the same kind of logic, this will work for the potential difference across the capacitor as well. We know that we're starting with 0, and we know that we are increasing. But because that increase in charge is proportional to the current, and the current is decreasing exponentially, what we're going to end up with is a graph that looks something... Oh, I haven't drawn that very well. Let's try that again. Is going to look something like that, where it increases quite quickly at first, but then eventually reaches that point there, which will be Q, we'll call that Q max, for the maximum charge that we're going to be able to store on the capacitor. Now, we can do exactly the same with potential difference as well, and it will be the same shape of graph. Now, to give you the equation that governs that graph then, and there's no way in the syllabus that you'd be expected to be able to derive this or anything like that, but to give you the equation, this equation becomes Q is equal to Q naught. Now, it does annoy me that the AQA call it Q naught, because to me Q naught means the charge at time is equal to 0, but what they say is that really this, I know I've called it Q max, but in the syllabus it's called Q naught. Now, I'm not going to argue about that too much. Personally, I wouldn't call it Q naught, but this is what unfortunately the syllabus tells me that I have to tell you. Anyway, so Q is equal to Q naught, and then it becomes 1 minus E to the minus T over RC. So we can see that it's very, very similar to the equation that we had for discharging. So Q is equal to Q naught, E to the minus T over RC for discharging. And for charging, we just replace that with 1 minus E to the minus T over RC. And then again, by similar ideas, we know that V is going to be V naught, 1 minus E to the minus T over RC as well. So just to sort of bring a lot of that together and to give you an idea of which equation we've got to use for which situation, we'll just have a quick summary table. So we've got charging and we've got discharging. We've got current, we've got charge, and we've got potential difference. So when we're charging, we use the same equation both times. So we use I is equal to I naught E to the minus T over RC. And we use the same when we're discharging. I is equal to I naught E to the minus T over RC. For charge, when we're charging, we use Q is equal to Q naught 1 minus E to the minus T over RC, whereas when we discharge a capacitor, we just go Q is equal to Q naught E to the minus T over RC. And then for potential difference, obviously that's the potential difference across the capacitor. We just use, it's the same as the charge equations, so V is equal to V naught 1 minus E to the minus T over RC, and V is equal to V naught E to the minus T over RC. So don't forget that that V there, that potential difference there that we're talking about, is across the capacitor. Now, just to finish off, we're just going to have a very quick look at how capacitors work in series and in parallel. Now, realistically, this is a little bit beyond what A-level or AQA expect us to do at A-level. I'm just going to include it for a little bit of sort of extra knowledge for you. It might be worth, especially if any of you guys are looking at some of the higher level universities, you can maybe go and have a look and see if you can prove that this is indeed the case, or at some point, if there's enough call for it, I might do this as an extension video at some point in the future. But anyway, let's have a look at series first. So let's take our two capacitors. Well, obviously we can do this with more than two capacitors. It's just easy to do with two at first. So we have C1 and C2. Well, when we have capacitors in series with each other, we use the reciprocal equation. So 1 over the total capacitance is 1 over C1 plus 1 over C2. And of course, if you have a third capacitor, you just add 1 over C3, etc., etc. For parallel, so if we had one capacitor there and another capacitor there, so again now we've got C1 and C2, and when we have capacitors in parallel with each other, our total just becomes C1 plus C2, etc. So you'll notice that, again, looking at things that we've looked at, stuff that we've studied in the past to do with series and parallel, you'll notice that the equations obviously look familiar. It's the same as if we had springs. So when we did materials, when we had springs in series or in parallel, obviously in parallel we add the spring constants, and if we have springs in series, then we use the 1 over equation, we use the reciprocal equation, whereas it's the opposite way round to resistors. We know that with resistors we add them in series and we use the reciprocal equation when they're in parallel. So as I said, those equations aren't really strange to you, they aren't new to you. We just obviously put them in a different context, and what you guys need to remember is that when you've got capacitors in series or in parallel, that the equations work out the same way round as they would with the spring constant in springs, and they work the opposite way round to how they would work for resistors. So here is your question for this video then. A 300 microfarad capacitor is charged using a 9.0 volt battery with negligible internal resistance in series with a 2.0 kilo ohm resistor. How long does it take for the potential difference across the capacitor to reach 8.0 volts? So as usual, pause the video at this point, go and have a go at that question and come back when you think you've got an answer. So in order to do this question then, we're going to use the equation because we're talking about potential difference and we're talking about charging. So you're going to use V is equal to V naught 1 minus E to the minus T over RC. Now, firstly, bear in mind that we're trying to find T. We're going to do a little bit of rearrangement first. So the first thing I'm going to do, I'm going to divide both sides by V naught. So V over V naught is 1 minus E to the minus T over RC. Now again, a little bit of rearrangement. The V over V naught we're going to subtract from both sides, and the E to the minus T over RC we're going to add to both sides. And what we end up with is E to the minus T over RC is equal to 1 minus V over V naught. Now at this point, normally I would suggest that you carry on with the rearranging, the algebraic manipulation, but actually at this point I'm going to make life a little bit simpler for us and focus on this right hand side of the equation. So coming over here, what we've got is 1 minus V over V naught. Well, we've got 1 minus, well, V is the potential difference that we want to know about, so that's 8 volts. And V naught is the maximum that we're going to get to, which is 9. So on that right hand side, that 1 minus V over V naught becomes 1 minus 8 over 9. Well, basic maths tells us that 1 minus 8 over 9 is just a ninth. So that gives us at least the right hand side of the equation. Coming back then, we've got E to the minus T over RC is equal to a ninth. Next stage then is that we need to take the natural log of both sides. So natural log of E to the minus T over RC is equal to the natural log of a ninth. And of course, when we get natural log of e to the something, they essentially cancel each other out. And what we're left with is that minus t over rc is equal to natural log of 1 over 9. Now you could work this through, you could then multiply both sides by RC and work it through, but I'm actually going to use a little trick here, which some of you may or may not know. If you have natural log of 1 over any number, that's just equal to the negative of natural log of the number itself. Now where that comes from, 1 over x we can obviously write as x to the minus 1, and then that power ends up coming down to the front. So what you've got in effect is minus 1 as the power times natural log of x, and that's obviously therefore the negative of the natural log of x, and all that comes, if you go back a couple of lessons, all that comes from the idea that the natural log of a to the power of b is b times the natural log of a. In fact, think about that, probably isn't in this series, that's probably in the Math Skills series. So if you have a look at the Math Skills video, especially on log analysis, just to remind yourself of that little law, and you'll find that in there. But anyway, coming back to it, the reason I'm going to do that is because negative of t over rc is the natural log of 1 over 9, can become negative t over rc is negative the natural log of 9. What that does is just gets rid of our minus signs. Now obviously if you didn't do that and you just worked it through, what you'll have found is that the negative signs cancel out anyway eventually, so we don't necessarily need to worry about it that much. Anyway, getting back to it, we're almost there. We end up with t is equal to rc times log of 9. And at that point we can start plugging some numbers in. So the resistance is 2 kilo ohms, so 2 times 10 to the 3, multiplied by the capacitance, which is 300 micro, so 300 times 10 to the minus 6, and then multiplied by log of 9. Plug that in through the calculator and obviously round it to the appropriate number of sig figs, which is 2 for this question, and what my calculator tells me therefore is 1.3 seconds. So to summarise this video then, obviously the main thing that we've looked at is the equations that govern capacitors when we are charging them, and we said that for the charge on the capacitor, Q is equal to Q0 1 minus E to the minus T over RC. For the potential difference, and remember, I'll say it again, just remember that's the potential difference across the capacitor. V is equal to V0 1 minus E to the minus T over RC, and current remains the same for discharging. I is equal to I0 E to the minus T over RC. Just remember that these Q0 and V0, at least from the context of what we're doing today, they are going to be the max Q or the max potential difference to do with the capacitor, so the max charge stored on the capacitor or the maximum potential difference across the capacitor. And then finally then for series and parallel, we said that if you've got capacitors in series, that we use the reciprocal equation, so 1 over the total is 1 over C1 plus 1 over C2, and if we have them in parallel, that we have C total is equal to C1 plus C2. So that's it for this video, and in fact that's also it for this series on capacitors. As usual, thanks for watching. I hope you've got something really useful out of that, and obviously that's useful for you and your studies revision, whatever you're using these videos for. Once again, thank you so much for watching, and I'll see you in a future series.